Okay, here's December 10th's recap video. We asked the question last week, what relationship, if any, exists between pressure and volume? We set that experiment up with a syringe, and we noticed that as you increase the volume, the pressure decreased, and as you decreased the volume, the pressure increased. We changed the volume by manipulating the syringe, and then we measured a change in pressure. So one question I could ask you is, which is the independent and which is the dependent variable? Check your notes and answer now. You should have noted that the thing that we measure is the independent variable, the dependent variable, and the thing that we change is the independent variable. Our controlled variables for that experiment were the number of particles, right? We didn't let any leak out, and we didn't add any, and we also didn't change the temperature at all. So when we came up with this graph, I said today in class that this graph represented an inverse proportion, or we said that pressure was inversely proportional to volume. So what is an inverse proportion? Well, first of all, let me point out here that this is what you should put or be able to state, and just say that pressure is inversely proportional to volume, and recognize that this graph represents this relationship. We said also in class that in our discussion that there were two reasons why this graph looks the way it does. One has to do with this mathematical relationship, and the other has to do with the fact that if you have zero volume, it would make sense that you can't, if you have a system that's worth measuring, like you have any particles at all, then you should never have zero pressure, right? I showed the golf ball, and we said that this kind of represents if you only had one single particle in your system, and you measured that, and you reduced the volume as much as possible all the way down, that you'd have a ton of pressure because the volume would be as small as possible for that single particle. And so you'd have just a ton of pressure. On the other hand, if you imagine making this box infinitely big and you have that one same particle, no matter how big you make the box, you'll still have the particle hit the side of the box at some point. So you can never get all the way to zero. So if we go all the way out, and you imagine this getting smaller and smaller and smaller and smaller, and these lines would keep getting closer and closer together to the x-axis, but it would never touch. Similarly, these would keep getting closer and closer and closer and closer, but never touch. So that should help you fill out why the graph looks the way it does. And you can state the relationship that pressure is inversely proportional to volume. But what is a proportion and what is an inverse proportion? I'm going to link a website in the description, and you can check that out more. But if you don't understand the way I explain it here, but here's a direct proportion. A direct proportion is when you have a graph that looks like this. Goes through the origin and then increases at some amount. And we studied a lot of these, and these always have this form y equals m times x. And you might have a plus b. You might have this graph shifted up or down, but either way, a direct proportion doesn't involve the plus b. And that's just a technical math thing. People are a little bit loose with the way they say that word direct means there's no b. But if we moved this graph up here, it would still be proportional. It just wouldn't be directly proportional. So what's an example of a direct proportion? Well, we had one in class, and that was the number of packs opened was proportional to the number of calories eaten, or the number of calories in the bag. And that relationship, so in that case we had calories over here, and we had number of packs here. And the rate at which it went up was that M. And so that relationship, the proportional relationship, is just how big is this, would determine whether how steep that line becomes. Same thing would be true if we had like the number of hours you work, if you're an hourly employee, is proportional. We say the number of hours worked is proportional to the number of dollars you earn. Right? That could look the same way. If we had instead money over here and your number of hours, the more money you make, the steeper your slope would be. The bigger this M would be. So the bigger your number of dollars per hour, or your hourly rate, if you had like a really high paying job, it would take you fewer hours to get to a bigger number of dollars. And so if you were really highly paid, it would look like this. If you were had a really cruddy minimum wage job, then yours might look like that. And to work a lot more hours to get the same money. So that's a direct proportion. On the other hand, in this video, we're trying to figure out like, well, what's the deal with this inverse proportion thing? Because that's new and different. So what's an inverse proportion then? If this is a direct proportion and this is an inverse proportion, all right, but why? An example of an inverse proportion would be like if you increase your speed, then your travel time will decrease. So it's kind of when things are flip-flopped. When you get an increase in one, you get a decrease in the other. As you decrease your speed, your travel time will increase. But you might be thinking, well, how come it doesn't just, like, why is it not just a straight line but going down? So if you remember back to algebra, maybe you don't, but this kind of graph doesn't come from y equals m times x. That's why we get an increasing slope. To get a decreasing slope, we have to say y equals negative m times x. So we're saying that instead of increasing by some amount, we're decreasing by some amount each time we increase x. So that's how you get this. So this type of graph comes from a different relationship. And it looks funny that it's not linear, but it just is what it is. So this would be, say, travel time and speed. So as you increase your speed, travel time decreases. And it can't decrease at a steady rate because that's not the relationship we have. All right, so back to the pressure versus volume stuff. If we change this to pressure and this to volume, that's just what we got. As we increase volume, pressure decreases. As we decrease volume, pressure increases. And we can represent that relationship as pressure is inversely proportional to volume. And as we increase the volume, we're decreasing pressure. And as we decrease volume, we increase pressure. If on the test you can recognize this graph and this relationship match, then you'll be good.